Hello everyone and welcome to another video of the Hidden Quantum Champions here on the School of Quantum channel. In today's video we are going to look at Zurich instruments. I'm not going to make a big mystery out of it because you already saw it from the title. And with that, let's grab something to drink, stay hydrated, and let's get started. So we are on the website of Zurich Instruments here, and you might wonder, why am I showing this? How is it related to quantum technology? Because you might know them, you might have never heard of them. They are making instruments, so lock-in amplifiers, for example, to measure signals. So as you can see here, there's some articles like, for example, IQM, Riverlane, then there's Zurich Instruments and NVIDIA, NVQ-Link. So there are some collaborations already that you can see here with Zurich Instruments and companies from the quantum computing space, so from the quantum technology space. Let's quickly scroll down the first page and then we go into the details of what they are actually doing, and I might also add some personal notes on that regarding how I've been actually working with those instruments in the past. So here you can see the various different instruments. So you see the smaller ones, there are also some bigger ones, and it goes all the way up to this big rack here, which is the QCCS. So we will learn about that, learn more about that in, I guess, a couple of seconds. It says quantum computing control system. So you see here this in this bracket notation logo here. It says compact and scalable to more than 100 qubits, productivity boosting lab 1 software, low noise, high resolution and large bandwidth, fast and flexible quantum feedback. And it says lock-in amplifiers, which I guess is like the standard product line. It says instruments from DC all the way up to 8.5 gigahertz, low input noise, high dynamic reserve, tools including boxcar, PID, scope, and FFT. And then you have the impedance analyzers here as well, which go from 1 millihertz all the way up to 5 megahertz in 1 milliohm to 1 teraohm. Measure fast and accurately, ideal fit for DLTS, MEMS, and ESR and ESL measurements. Now, there's a couple of interesting points in that, but maybe let's take a couple of steps back. I will start with some information on my personal experience. So when I was still working in the lab, and there's like different labs that I worked in, there were also labs I collaborated with. There's a couple of standard instruments that you always need when you want to do any type of, let's say, materials research, like quantum materials research, superconductor measurements, spin qubits, whatever. Like there are a couple of instruments that you always need, and one of them is the lock-in amplifier. So the lock-in amplifier uses a special technique by basically creating a permanently fluctuating signal. So like an AC, actually not fluctuating, more oscillating signal. So an AC signal, and it basically tunes to a specific frequency, and doing so you can basically get a very high signal to noise ratio if you play the trick of using a fast Fourier transformation. So what does that mean? Think of noise as some fluctuations on your signal, right? So you're measuring a constant signal and there's some noise on top of it which is fluctuating. Now, if you had a specific frequency, so let's say you have a signal which goes like this, so some oscillating signal, and on top of that you have now this noise, then you can basically use what is called a Fourier transformation. So you can filter out only this specific signal here, and then you only get the amplitude of that specific signal. And by this you can basically filter away a lot of the noise. And this is a technique which has been invented already quite a while ago, discovered quite a while ago. And there are a range of manufacturers of this type of technology out there. So in the old days, which is even until today, this technique has been done or has been realized using classical components, so circuit components like resistors, of course, amplifiers, but also impedance, inductivities, capacitors, and things like that. And you can actually do a lot with analog techniques already, so you don't even need any digital way of processing this signal. And that's basically how these log-in amplifiers used to work. And even today in a lot of labs, they still being implemented like this. Usually they're like big boxes. You see them sitting close to the cryostats in the quantum labs, but yeah, that's basically what it looks like. But also in the optics area, when you're dealing with very small signals and you want to reduce the noise, you use these log-in amplifiers. At the backside, they come with with a big bus connector, because it's an older technology, and then you can hook up multiple of them in series and so on. So that's like the typical good old lab setup. Now, at some point, we decided to buy these Zurich Instruments log-in amplifiers, and there are so many things. Like, this is really basically thought differently from scratch, as in, okay, do you really need to have this old bus connector still? No. So what they did is they basically put a Ethernet connector on there, which is already, let's say, new for, or was for us, something that we only had a very limited number of instruments that had that. But it's very cool because you have a very fast connection. You can send a lot of data back and forth with this. So suddenly you are not limited anymore by, let's say, the bus connector. The boxes are much smaller, so you can fit more of them in the same space. And they actually use underlyingly a more, let's say, a digital technique, I would say, which is FPGAs. So field programmable gate arrays. So basically you can program what the log-in amplifier is doing with the signal. And this literally enables you to do many additional things than just, let's say, with a normal analog log-in amplifier. Like, for example, you can read the full frequency spectrum. So instead of just doing a fast Fourier transformation on a specific signal, you could read the full spectrum by basically sampling at a very high rate, like on an oscilloscope. You measure the signal at a very high rate, so you see the whole fluctuations, and then you transform it into the frequency space, and then you will see, let's say, one peak where your log-in amplifier is tuned to the signal, but you will also see other peaks around, for example, due to noise, which is in your system. So you can analyze the noise spectrum. So that's a very helpful thing, because doing so, you can tune the frequency to a value that is, let's say, very far away from all of the noise sources, enabling you to generate, let's say, a very clean signal. In traditional log-in amplifiers, you, for example, have to know that you don't want to be, in Europe at least, you don't want to be at 50 Hertz, because that's where the frequency from the socket is coming from. And there's usually a lot of noise in this, and then also, of course, in the multiples of this. And now with this log-in amplifier, for example, you could analyze this. So that's very cool feature. Of course, there's also other stuff. You have a very broad frequency spectrum. So as I mentioned here before, it goes basically from DC, so no frequency, all the way to 8.5 gigahertz, which is quite a high frequency. So you have that, and then there's a lot of other stuff. And I think also from a business model, I found it very interesting, because you can buy, let's say, the standard log-in amplifier box with the standard functionality. But later on, if you say, for example, I don't know, I need the FFT functionality, you can actually book it, and it comes via a software upgrade to your system. At least it used to be back then when I was working with that. And I found that very cool, because it leaves you the option to very easily upgrade your system. But of course, there's also this arguable question if, like, okay, should that be possible to just have a software upgrade? Like, that means technically the functionality is already in there. But then I would say probably technically you can also just use the data acquisition and then run the calculations yourself on that data. So you basically pay for somebody else to implement the algorithm in a very neat front end for you. That's the other thing. It mentioned here the Lab1. I don't know where it is, but here, the Lab1 software. So that's also very cool. These systems, they come with a very nice software interface, which means one, you can basically control it via browser. So you connect it via your Ethernet plug, and then you can open in your browser a web interface where you can basically control the login amplifier. So you don't need to click any buttons anymore. If you look here at the pictures, there are also no buttons anymore on these devices because you don't need them. You have a computer sitting there. And by the way, that's what the interface looks like. So you can see here very nicely how the signal lines are going. I remember you could also look here for the different channels. So sometimes, depending on the configuration you have, different channels might have different of these elements in here, and then you can really tune like for every single channel, amplification stages if you want to have filters in there, and so on and so forth. So that's really like catering to this capability of using the software and then changing all the options and giving an additional, let's say, optical overview of what you're actually doing. In the old way, you would always have to first understand which button is doing what, and then you press different buttons on the login amplifier. Usually there's also like a shift button, and then you have even more buttons, and there's knobs which you can turn, and you have to first understand what you're doing. And then if you're turning the knob in the wrong way, you might ramp up the voltage and destroy a sample. And these things you can hear really nicely in the software actually mitigate or make sure that these things don't happen. Also, and that was also very important for me back then, it comes with various different API interfaces, and I guess we will also see more about that when I go here through the product pages. But basically, those API interfaces, they really cater towards, let's say, modern software development. So you can basically access the system from a Python API, for example. And I think that's useful because most of the data acquisition frameworks are also in Python. And just as an example, we in our lab, we used to use Q-codes. And you also find some old tutorials of mine here on the channel where I explain how Q-codes used to work. And there's also, for example, a driver implementation of Zurich instruments for Q-codes, which basically makes it very easy to also use the instruments with lab automation software. And I think that's also available for other software frameworks. So also on the software side, I really think that what they've been doing, what they've been building is making it easier to work with the instruments and is making it faster to go from product acquisition all the way towards generating the first results. And I guess that's what counts. So generating first results and then also doing a lot of insightful measurements in a fast and automated way so that basically you utilize the time where your sample is cooled down in the maximum, most efficient way possible, right? At least it used to be for us kind of the measure. You want to make sure that your cryostats are up most of the time, and you want to make sure that whenever a sample in, measurements are happening and there are no gaps in between. That way you utilize at an optimum your existing lab infrastructure, which is important because lab structure and utilization in a way also correlates to publication because you need data to publish, at least in the experimental world. And then obviously the publications also play a role in how well your research lab is doing, right? And how well you can receive funding. Okay, so here's some information about Lab 1. I'm not going to open this video now. There's some customer interview here as well. And then down here we see something about the applications that these devices are being used in. Quantum technologies is what we are going to look at today in a later part of this video. There's also the more classical impedance measurements, optics and photonics. I mentioned that previously as well. Scanning probe microscopy, so for example STM and I guess also AFM in a way. There's nanotechnology and material science, so Again, that can also be in a way related to quantum technologies when you look at material science, like cooling down materials that are like super thin layers of something very specific where you need very small signals, but also nanotechnology as in development of new semiconductor in architectures, like transistor architectures, like nanotube transistors, where you have to have very, very tiny signals and then measure them with a very low noise. And the same is true for sensor development. Finally, down here we find the Meet Us At section where they are pointing towards the events that I guess they will be present at. I'm recording this beginning of November, and we are seeing here there's like a couple of events happening here in November in the United Kingdom and USA, so also like globally present and very much up to date. And then of course finally we have all the links down here. There's a way to subscribe to their newsletter and follow them on social media. Okay, let's quickly check out the different products. I will just go through the overview because I think otherwise this video is getting way too long again. But we see there is quantum computing control systems, so systems that are actually catered towards quantum computing control, so quantum computing in particular. Then there's lock-in amplifiers and impedance analyzers. I mentioned that before. Arbitrary waveform generators, or AWG. Then there is add-on options that I also mentioned before, product finder, and there's some information here about Lab1, the software package, and Lab1Q, which I guess is the software that is catering towards the quantum computing control system. On the applications, it says quantum technologies, impedance measurement, optics, and photonics. That's what we've seen already previously down at the lower side of the page. There's some other resources here as like webinars, white papers, tutorial, application notes, application briefs, blogs, user stories, and publication. Maybe a quick note also on that. Already back then when I was working in the lab, Zurich Instruments had quite a couple of videos on YouTube, and I also usually found them quite insightful because you could see, let's say, how to set up a basic application without having to read through all of the very extensive documentation. Also these white papers, I remember I used one, I think, on how to measure the quantum Hall effect. So I looked at, basically it was like a white paper tutorial explaining how to connect the different ports of your Zurich Instruments lock-in amplifier, I think, or even two lock-in amplifiers to get some high quality measurements of a Hall bar structure, which is, let's say, a typical structure that people are using in materials research. There are also some tutorials here. I think back then they didn't have that. Maybe it was also an application note. I'm not sure if it was a white paper or an application note. There are also some briefs, some blog user stories and publications. So there are also some people quoting Zurich Instruments in their publication so that you know that like this measurement has been done with this type of control system, with this type of measurement system. There's this section on support here, and there I quickly just want to mention that there I also used to have a very good experience, and I'm not sure if it's still like this, but really back then I remember when we were buying some of those units and setting them up in the lab, and back then we hadn't bought many of them. We later on bought more of them because of this positive experience, but I remember I had some questions and I was reaching out to the Zurich Instrument support. And actually, somebody reached out to me and asked me if we could have a video call so they could walk me through the different stuff that I need for my measurements, and they could also help to optimize the measurements themselves. So I remember that to be a very positive touch point. Then also one time we had an issue with a submodule in the system, and that was also very promptly being exchanged. So also that part of the support I found very positive back then. There's also some information on the company, which we will check out later. Now I need to really check quickly this quantum computing control system part here, because I'm not familiar with that one and I would like to also learn a little bit about that. So here it says quantum computing control system. In 2018, Zurich Instruments introduced the first commercial quantum computing control system, QCCS, designed to control more than 100 superconducting and spin qubits. Each component of the QCCS is conceived to play a specific role in qubit control, readout, and feedback, and operates in a fully synchronized manner with the other parts of the system. Lab1Q, the Zurich Instruments control software for the QCCS, provides a full measurement framework for quantum computing and facilitates the integration into higher-level software. The Zurich Instruments QCCS supports researchers and engineers by allowing them to focus on the development of quantum processors and other elements of the quantum stack while benefiting from the most advanced classical control electronics and software. And quick open bracket here. This is something that I also mentioned previously with other of these companies here in the Hidden Champion series. So a lot of these, let's say, commodity providers, as in providing, let's say, the peripherals, the framework that you actually need to do quantum computing, they have this approach here where they basically create something that caters towards, I don't know, the quantum computing, so that, let's say, if you are a quantum computing startup, you don't have to reinvent the wheel throughout all the different disciplines, but you can really focus, let's say, on generating your specific qubit technology and not having to invent the cryostat, the measurement electronics, and what like the filter stages that go around it, and all of these different things that you might need, the cables, the turbomolecular pumps, whatever, right? You don't want to invent all of this again and again. You might want to focus on the chip, or you might want to focus on creating a quantum error correction algorithm, whatever. And then you want to really make sure that everything else is done by the specialists. And this is the same here. So the QCCS is supposed to be a self-contained, as far as I understand, a self-contained system which does the whole control of the quantum system, like sending signals in, reading out, and things like this, controlling the system, performing the gates, and so on. And that way, as a quantum scientist, I guess you can focus on designing the chip and then, of course, tuning the system in a way that it can interact properly with your chip. But you don't have to, let's say, create any APIs that then, let's say, have higher level abstractions that then do something specific. And I guess we will learn more about that when I read further down here. So back to the text: efficient workflows, tailored specifications and feature sets, and a high degree of reliability are the characteristics most valued by our customers. The scientific achievement accomplished with the QCCS, see below for a list of publications, are a testimony to our close engagement with some of the most ambitious research groups in this area. The QCCS operates directly at qubit frequencies without mixer calibration, offers high density and low cost per qubit, and provides a growing feature set that takes into account the most recent developments in quantum computing. So that's exactly what I mentioned. So this is control electronics that is highly optimized to this use case, so you don't get any extra features that you will never need. And that's also something that I found interesting now. It says provides a growing feature set. So basically somebody or a group probably at Zurich Instruments is following the developments in the quantum computing world or in the quantum computing research, and then also implementing probably like calibration features. We talked about error mitigation schemes. These type of things I would expect are kind of implemented on a software level into the system. Key features: scalable design, new inputs and outputs can be added at any time, and the high channel density and consistent performance are guaranteed for all setup sizes. Productivity boosting software, so the Lab1Q efficiently connects high-level quantum algorithms with the analog signals at a quantum device. Hardware specifications that match the application: low noise, high resolution, and large bandwidth. Thought through and tested system approach, precise synchronization, reliable operation. And then there's also feedback operation, fast data propagation across the system, powerful decoding capability. And then here, I guess we see the different key areas. So you see the system control, operation as a single instrument, synchronization, and real-time operation across the entire system. That's also something important to mention. I remember that, like on the back side of these Zurich instruments, lock-in amplifiers, there were like multiple Ethernet ports, and you could also use some of them to synchronize the systems with each other so that like their clocks are synchronized, and then you can really make sure that, in certain setup where you need multiple of these systems, they are actually perfect in sync. Parallelization and queuing of tasks to minimize idle time on the quantum device. That's again catering to, let's say, highly efficient use of existing hardware that is cooled down, interfaces for other quantum frameworks. That's also something I mentioned, as in, for example, Q codes, and I guess they also have other ones here. There's qubit control, so access to maximum gate fidelity, low noise, high bandwidth, high stability. Again, that's like, I think I mentioned that also previously in this episode with other instrument manufacturers. If you want to flip your qubit from one state to the other, you need to apply some type of signal. And if you don't do that very exact, like let's say your qubit doesn't flip like this, but more like flips only like this, then you will accumulate some error here. So then you start to get some precision in the system, and that will spread across the whole system and of course make then the whole operation very difficult. So that's why you need to have something that has not only low noise, but also high stability and very good repeatability also, right? Then there's qubit readout, up to 64 qubits per instrument. And then quantum feedback, that's I think also something that we talked about before. Including ultra low latency down to 50 nanoseconds. Wow, that's quite an achievement. There's more information down here, and I invite you to check that out in case you're interested. What I also find interesting here is there's the related application notes also linked. I remember that I think what I read back then was an application note, and there are also publications. I mentioned that before. Some publications they mentioned they are actually using Zurich instruments, and there you can find relevant ones. Let's quickly look into the quantum technologies application space. There are quite a few here. So we have overview on quantum research. Let's quickly click that. That I guess gives us an overview over the different areas. So here we see platforms and technologies, superconductors with the transmon qubits, bosonic qubits, and fluxonium qubits. There's the defect centers, so like NV, nitrogen vacancy centers in diamond, silicon vacancy centers in diamond, and rare earth ion doped crystals. So that's about like putting some doping atom, so an atom that usually does maybe one step back. If you have a material like silicon, just purely silicon, then it will form a crystal. So if it's at room temperature and you're doing it in a proper way, like you can grow it into a crystal shape. A little bit like you might remember that still from school time, where you had this solution where you put like salt inside and then you can draw a crystal out of it. Similar things are being done when creating those silicon wafers. So they're crystals. And now these silicon vacancy centers, or the nitrogen vacancy centers, NV centers, there you basically add something, or rare earth ion doped crystals, you add an atom into the crystal that is not, for example, silicon. And that way you have, let's say, an isolated atom inside a crystal, and now the crystal is a very rigid structure, so it's very stable. If you put temperature on it, like you probably know, diamonds are very stable. They are very hard and they are very stiff. So they are actually like a cage that you put around this, for example, single atom here. And now the single atom is a basically isolated quantum system. So you can manipulate that, for example, optically, because the crystal is transparent. And that way you can, let's say, create a stable quantum system, even at room temperature, that you can then measure and investigate. And then finally, there's also semiconductors here. This to me looks like a nanowire with some gates on it and some gate fingers here to manipulate it. But also there's gate-defined dots. There it says nanowire, gate-defined dots. So that's a topic for another video, I guess. And all of these applications, they require lock-in amplifiers, like for example, the ones from Zurich Instruments. Here's the capabilities and features also listed. I think we've talked about them a little bit before. And here are the benefits. So simplify your setup. That's something I mentioned. Speed up your software workflows because of the API interfaces, right? Get state-of-the-art signal quality. That's also, I think, something we briefly touched. Benefit from our application know-how, so the documents provided, but also possibly the support, and then shorten your measurement time. Okay, because that's maybe also something to mention. I'm not sure if this is referring to that specific thing, but if you have a lock-in amplifier that can go up to 8 gigahertz, so the frequency scales inversely with the measurement time. So if you only measure at a oscillation of 1 hertz, you want to average across multiple of these oscillations, so you have to wait a couple of seconds. Now, if you're measuring at 10 hertz, you have 10 oscillations every second. So if you want to, let's say, average across 10 of them, it's 1 second measurement time. If you have 100, then it's 0.1 second, and so on. And then if you go up to 8.5 gigahertz, so remember there's kilo, mega, giga, so this is 10 to the 9 hertz, then you can go much faster. So you can sample much faster, and that means you decrease the measurement time. I'm not sure if this is what is being indicated here, but that was my experience. Good. So let's quickly check out one of those. Just simply we take the superconductors and then we just check out what we can see here on the page, because I don't want to make the video for much too long now because it's already quite long. So it says quantum computing with superconducting qubits. There's an application description here. What challenges do we help our customers tackle? Qubit control, qubit readout, quantum feedback, scalable quantum control. There is a scheme here, and that's what I was mentioning before. So that kind of helps you to understand what instruments would you need and how would you set them up to do, let's say, an optimum setup for measurements. Here you see the qubit chip with all of the different qubits, in this case 12. And then you see the different components here that you would need and how you can kind of set them up. You see here, for example, this arrow which indicates that these two are being, I guess, synced. You see there's like a clock happening here. So all of these measurements, they are somehow connected and synced with each other. And then it also shows like how you set up, for example, the signal generation from the different devices and how you actually read out the signals for this specific use case. It tells you qubit characterization and calibration, so like how it actually works, what are the features, what is the benefit, and some other information here about this specific setup. There's also some information on the programming resource. Here again, you can use the lab1q, and then some product highlights. I guess these are the products that are featured up here, right? You see there's the HDAC, then there's SHFSG, and you can see down here there's the HDAC and there's the SHFQC and the quantum hub, and I guess these are also the ones that are being used in this tutorial up there. There are also some more information why you would use Zurich Instruments. You can order a quote here. You can have some videos that are explaining you the different features of these different instruments. There are even webinars which you can watch, which are very much catered towards this application. So here you see hands-on superconducting qubit characterization. So that's like very on point for this specific thing. So I guess if you are lab looking into one of these applications, I guess you can really just follow the guides more or less here. There's related blog posts to that, various different ones. You can also see they are in collaboration. So we've seen Quantware as one of the other companies that have been featured previously in this series. There are application notes down here and then also related publications. And if I just look at them, I'm already interested, and I think I should start reading some of those because, yeah, that all seems like very interesting developments that are interesting to follow. But we don't have time for that now. Good. Let's quickly end this by checking out the About Us part in the company. So our story, Zurich Instruments is a test and measurement company headquartered in Zurich, Switzerland, more or less neighbors of me, and is part of the Rohde & Schwarz family. We develop and sell measurement instruments worldwide, either directly or through carefully selected partners, and provide responsive and effective customer service. We are a growing, standalone and founder-led company. What we do: Zurich Instruments makes cutting-edge instruments for scientists and technologists who work in advanced laboratories and are passionate about phenomena often difficult to measure. Our offering includes lock-in amplifiers, arbitrary waveform generators, impedance analyzers, phase-locked loops, digitizers, boxcar averagers, and quantum computing control systems. We believe in the power of system integration. System integration leads to reduced setup complexity and more efficient workflows, better time allocation, and more reliable measurements. Our instruments deliver market-leading specifications for sensitivity, dynamic range, feature set, speed, and accuracy, as shown by Zurich Instruments industry firsts. And then there's a list here, 2009 to 2018, I guess, with the big technological advancements that they have made. And then here we see, as the time goes, I don't know, maybe that's the number of employees that are working there, I'm not sure. And then 2019 to today, there's some more story. Where we come from: Zurich Instruments was founded in 2008 by Dr. Sadiq Hafizovic, Dr. Flavio here, and Beat Hofstetter as a spin-off from the Swiss Federal Institute of Technology, ETH Zurich. At ETH Zurich, they developed a prototype used by a team of biologists to characterize and sort blood cells using single-cell impedance measurements. The instrument had to be capable of simultaneous high-rate demodulation at multiple frequencies. The solution relied on an FPGA-based digital signal processor and sophisticated software, and it replaced a much bulkier and complex setup. That prototype became the foundation for the first line of highly integrated multifunctional equipment for time and frequency domain analysis developed by Zurich Instruments. And that's also something we talked about before, so this FPGA technology. So how we do it: we integrate state-of-the-art analog electronics, high-precision digital signal processing, innovative software, and an intuitive user interface into a line of products guided by lean design principles. Integration does not stop at the instrument level, however. Our products come with responsive and effective customer service, a high level of professionalism and competence, and complete documentation. Where we are going: our measurement systems feature in a broad range of demanding applications around the world. We are inspired by customers who are global leaders in scientific and industrial research and development, by our external partners, and by each other. Zurich Instruments has a pipeline filled with projects and innovations. We are open to our new partnerships, collaborations, customers, and team members. Okay, with that, I think I will stop here. If you like this video, as always, please make sure to give it a thumbs up. And if you don't want to miss out on the next hidden champion in this series, which is catering to the whole world of quantum technology with something that you might have never heard about before, then make sure to subscribe to this channel. As always, stay hydrated and see you in the next one. Bye bye.